Hello learners, welcome to Unacademy. My name is Mohana. I'm a physics educator here. So just a second, let me just check if I'm online. Okay, so in today's class we're going to cover an important topic from ray optics. We're going to learn about the mirror formula. Okay, so before we derive the mirror formula, we will learn what are spherical mirrors and what are the types of spherical mirrors, some definitions regarding spherical mirror, and then we will derive the mirror formula. All right. Now once again, my name is Mohana. I'm a physics educator here at Unacademy, and basically I have my master's degree in physics. And this is my Telegram channel, so you can follow me on my Telegram channel. Before any class goes live, I share my link. And this is the common ICSE and Unacademy and ISC and ISC common channel, so you can follow this channel as well. Good evening, Isha. So first we'll see what are spherical mirrors, right? So a spherical mirror is just a reflecting surface which forms a part of a hollow mirror sphere. So take a hollow glass sphere, okay? So in this, just cut a part of this hollow glass sphere over here. Okay, what we're going to do is we are going to cut a part of this hollow glass sphere. Okay, so if you cut a part of this hollow glass sphere, what you get is basically a spherical mirror. Okay, so you get a spherical surface from here. Now, so the spherical mirrors are itself a part of a hollow spheres, and now that you have the spherical mirror, right, mirrors means always one side of the mirror can be polished, right? So depending on which surface you're polishing and which surface becomes a reflecting surface, the spherical mirrors can basically be given as two types. Okay, now in case, let's say you in this particular case, a spherical mirror in which the inner hollow surface is silvered. So inside surface over here is silvered. Okay, so if the inside surface over here, right, the inside just a second guys. Okay, so the inside surface over here is silver. Okay, so if the inside surface is silvered, means then obviously this outside surface that we have over here would become a reflecting surface. Okay, now such a mirror is basically called as a convex mirror. Now obviously the reverse you can also try, we can also do the reverse, right? So right now if you actually silver the outer surface such that the inner surface of this mirror becomes a reflecting surface, then we call such a spherical mirror as a concave mirror. So spherical mirrors are just part of a hollow sphere glass. Okay, take a part of this hollow sphere glass, right, just cut this, take a part of it, then what you get is basically a spherical mirrors. So if you actually end up silvering the outer parts, okay, inside surface, then obviously the outside surface over here becomes a reflecting surface, then that is a convex mirror. Similarly, again, if you see, if you take the if you silver the outside surface such that the inner surface over here becomes a reflecting surface, then it becomes a concave mirror. Concave mirror, just remember as walking into a cave. Okay, so the reflection happens from the from basically the bulge, not from the outer bulge surface, okay, but from inside the surface. Okay, then we call it as a spherical mirror. Okay, these are again mirrors. So what what we see over here is basically reflection. Now there are some definition connection that are in connection with spherical mirror. So let's take a spherical mirror. Okay, so this spherical mirror, if you see, it was part of a hollow spherical glass surface, right? So if you take the spherical mirror, let's give it a name. Let's say this surface is basically okay, A, and this curved surface is AB over here. Okay, now the center point over here, the center point of this mirror, we call it as a pole. Alright, now this glass surface, this spherical glass surface is also a part of this this is basically a part of the hollow sphere, right? So this particular hollow spherical shell sphere over here has a center, right? So what is the center point of that glass sphere? So over here, if you see, what is the center point of this glass sphere over here? Okay, let's say this is the center point over here. This point of the glass sphere is called as center of curvature. Okay, and from here to all parts of the side, right, from here, from the center of curvature to all parts of the edges of this glass surface, we call that as radius of curvature. Okay, so obviously since this mirror is a part of this spherical surface over here, right, the center part of this particular surface that we have over here, the center part is basically called as the center of curvature. Okay, and if you see from the distance from the center of curvature, okay, to this distance to B, okay, or from this A to C over here, or even if you see from C to P, all of these we call it as radius of curvature, and radius of curvature we give it by R. Okay, now this is center of curvature and then we have radius of curvature. Now if you draw a line connecting the pole with the center of curvature over here, alright, if you just draw a line connecting the pole with the center of curvature, okay, this line that we have becomes our principal. Just a second, it's okay. Okay, this line that we have in this case, if you just take the line connecting the pole and the center of curvature of the mirror, then this line becomes the principal. Okay, sorry, just a second. Principal axis. Alright, so here what we have, very simple, pole is basically the middle part of a spherical mirror, center of curvature is a sphere of which this mirror forms a part, obviously, right, the center of curvature is a sphere of which the mirror forms part, basically which the mirror forms a part. Radius of curvature, if you see, in this case, if you see the distance from B to C or from C to A, right, from C to B, all of this from the center of curvature to this mirror surface, anywhere on the spherical mirror surface, right, outer surface, if you see, that's radius of curvature. Okay, now the line passing through the pole and the center of curvature of the mirror, we call it as the principal axis. Okay, so these are the basic definitions we need to know. And apart from this, if you see, if you take this length AB over here, this length we call it as, okay, linear. This length over here we call it as linear aperture. AB over here we call that as linear aperture. Okay, linear aperture just talks about the size of that particular mirror. Okay, it just gives the diameter of the boundary over here. Okay, so it just talks about the size of the mirror. Okay, so this is linear aperture. So for example, let's say you have a spherical mirror of this size and or have a spherical mirror of again of this size. This has a larger aperture than this one, right? So it basically aperture talks about the size. Now if I join from this end to this end, right, from the curved surface to here, if I join, this is linear aperture. Okay, then this bulged surface that we have is basically angular aperture. Okay, so in this particular picture, if you see, if you look at A, B, okay, A, B, A, if you take this particular point, okay, okay, so if you look at this angle over here, okay, A, C, B over here, okay, look at this angle that we get over here, right, this angle suspended, okay, from the center of curvature towards the surface of the mirror. What is the angle suspended? That becomes angular aperture, because, okay, that angle gives you angular aperture. That just tells you how, again, what is the size of the mirror. Now, apart from all of this, right, now let's say we have a mirror. Let's take both cases. That is, for example, let's say in this case we have a concave mirror. All right. So concave mirror, if you're taking, obviously what we see, that the inside surface becomes reflecting. Concave, think of walking into the cave. So this side is reflecting surface, right? Now any ray, if you see, okay, any ray that comes parallel to this principal axis, right? So over here what we have, this is basically pole, right? This is basically pole and this is a principal axis. Okay, now any ray that comes parallel to this principal axis over here, okay, so obviously it's a mirror, they will get reflected and they will pass through the focal point. Okay, focal point of this particular mirror over here. Okay, now if you see, take another ray that is basically coming parallel to the surface again, right? Any ray that comes parallel to the surface over here, again they pass through the focal point, right? So if you see, all of these rays that are incident on this mirror converges. In this case what we see, they converge at a point. right? The point where they converge, where all of these rays converge, is basically called as a focal point. Now any ray, let's say this is basically the center of curvature, right? Let's say this is hello Arnav, if let's say this is focal point, so let's say this is center of curvature, okay? Now any ray that is passing straight through the center of curvature, okay, and if it is going straight towards this pole over here, whatever was this angle of incidence, it will return back in the same angle. Okay, so if you look at where all these rays are converging, okay, this point is basically called as this focal point, and if the rays are converging, then we call such a focal point as a real focus. Okay, obviously in this case what we have is a concave mirror, right? This is basically a concave spherical mirror, right? So this is for a concave mirror, the focal point, the focus is basically real. So there would be, what about a convex mirror in this case? Okay, very simple. Let's take a surface. Let's say we have a convex mirror. Okay, now this side, the bulge side, becomes the reflecting surface, right? So again we have the pole of the mirror. Now in this case, because this side is basically reflecting, what will happen? Any ray that is parallel to this principal axis, okay, it comes parallel over here, obviously they get reflected, right? Now even if you take another ray, they come parallel over here and they get reflected. But we just saw any ray that comes parallel over here, see, all of them converges at a point. In this case what we are seeing, they are all diverging. So what we are going to do is, in this case we are going to extend this ray, okay, such that they meet at a point, all of them converge at a point, okay? But in this case again, any ray that is going parallel, let's say this is center of sorry, this will not be center of curvature of the mirror, this side won't be the center of curvature, because this is part of this spherical surface over here. Center of curvature would lie on the other side. Center of curvature in this case, if you see, because this is a part of a spherical mirror, right? If you're taking this as a part of a spherical mirror, then obviously center of curvature would be somewhere over here. Now in this case what we are saying, all of these rays are diverging, but okay, but we can extend the rays to meet at one particular point, okay? Now this point where all the rays appear to converge, this is again called as the focal point, and this focal point is nothing but, in this case the focal point is a virtual focus. Why? Because the rays are diverging, okay, and we are extending the ray to meet at a point, okay? This is virtual focus. Now, so a convex mirror, if you see, okay, it has a virtual focus, okay? Alright, now if you take a plane, right, if you take a plane, okay, now one more point is, from the pole to this focal point over here, from the pole to the focal point, okay, this distance we have, that's called as the focal length, okay? In this case, from the pole to this focal point, what the distance PF, in this case what we have is the focal point, okay? Now any distance measurement you make with respect to mirrors over here, okay, you have to choose from the center of from the pole over here, any distance measurement. So if you want to measure the focal length, so you have to start measuring from the pole towards this focal point, okay? Now other than this, if you see, if you could just draw a plane where all of these rays are converging, okay, this plane that is basically perpendicular to the principal axis, where the rays are basically focused, right, this plane is called as principal focus, okay? So these are some definitions with relationship to with the relation to mirrors, okay? Now let's see, there's some sign conventions that we are going to take when we basically when we work with spherical surfaces, when we derive this particular mirror formula, we have to take certain sign conventions, okay? So again, let's say this is the surface of the mirror over here, alright? All distances, any distance measurement has to be done from the pole, okay, or has to be done from the pole. Now let's say the object is somewhere around, let's say the object is somewhere around here, okay? Let's say this is the object, okay? So the rays from the object goes in this direction, right? So this is incident ray, okay? This is incident ray. So let's say all distances has to be measured from the pole, right? So this is where the object is. Now we want to find what is the object distance. So what do? We go from the pole towards where the object is, right? We go in this direction. Object distance is given as u, okay? Now incident ray is in this direction, that is the ray that is coming out of the object, right? Incident ray is in this direction, right? And if you see, object that you're taking is in the opposite direction, right? So any distance measurements that is taken opposite to the incident ray, if you see, they are given the sign convention negative. Okay. Now again, let's say for this particular case, let's say the object is the image is formed somewhere this side over here. Okay. The image is formed, let's say somewhere on the somewhere this side over here. Okay. Alright, let's say this is image. Now if you see, to measure this particular distance, okay, so we start at the pole and this is where the image is, so we have to end up going in this direction, right? So this is the direction of incident ray, and to measure image distance we are going in the direction of the incident ray, right? So in this case, if you see, image distance we take it as v, so according to sign convention this value is positive. Okay, why? I'm really sorry, positive. Why? Because any direction taken in the direction of incident ray is positive. Alright, now measurements made in the direction of incident ray is positive against the incident ray of negative. Similarly, any distance measurements made above the principal axis is positive. Any distance measurement, for example, height of the image, any distance that's made below the principal axis is basically negative. That's it. This is a sign convention. All this you need to know about sign convention that's it. Okay. These are the 4 points you need to remember. Now, just a second, guys. Give me 1 second. Alright, now let's do the mirror formula. Now the mirror formula in this case, if you see, it just gives a mathematical relationship between object distance that we saw, okay, from the pole where the object is placed, image distance from the pole where the image is kept, and the focal length of the spherical mirror. Okay, so the mirror formula itself is 1 by focal length, 1 by f is equal to 1 by object distance plus 1 by image distance. This is all we are trying to derive right now. Okay. So, one more relationship you need to note in this case is a very simple one. Okay. So, I said where all the rays are basically focused, right? We call that as the focal point, right? This is basically focus. This is the focal point, right? Now, and from the principal pole to the focal point is focal length. Now, if you see, from the center of curvature to pole, any distance you take, that is radius of curvature, right? So, radius of curvature, if you see, is basically twice the focal length. Okay. Now, that is from here to here is focal length, right? Let's say, for example, this is 1 centimeter. For example, let's say this is 1 centimeter. Now, from focal length to C is again 1 centimeter. So, these put together from P to C, what is the distance if you see? That is radius of curvature. That is basically twice the focal length. So, this is 1 centimeter, together if you see 2 centimeters you will get. Okay. So, focal length if you see is always, for example, I took it as 1 centimeter. So, focal length is always twice the radius of curvature. Okay. Knowing that, let's go ahead and do the mirror formula. But before we do that, we need to know one more thing. That is, how when you have a convex lens, how an image is formed. We are going to do the mirror formula for a convex mirror. Okay. Sorry, not a lens, mirror. Okay. So, again you need to know certain, to draw the ray diagram, okay, you need at least minimum of 2 rays. Okay. But we will see 3 conditions. Now, we have an object here. We have a convex mirror. Convex mirror means this outside reflecting surface. This outside surface is a reflect surface. Inside is polished. Now, any ray that comes parallel to the principal axis over here. This is the principal axis, right? So, any ray that comes parallel to the principal axis will always be reflected back. Okay. So, in this case, to find what is the focal point, we have to extend this ray over here, line on to the other side. Okay. So, this center point which we have is basically the pole. Now, any ray parallel to the principal axis passes through the focal point, right? Now, any ray that passes through the center of curvature, right? Let's say in this case, this ray comes and hits and let's say if you extend the ray, we can see that it passing through the center of curvature. Okay, so for this mirror surface over here, because it's a convex mirror, concave mirror, right? For this mirror surface over here, this side becomes inside the mirror, right? What we have is the center of curvature. Now this surface over here, if you see, any ray that comes, that is incident towards this center of curvature over here, any ray coming towards the center of curvature will be reflected back along the same line. Okay, 2 rays are enough to do the ray diagram, but we will see one more law. Okay, now any ray that is incident towards the pole, whatever this angle of incidence is, okay, let's say whatever this angle of incidence is, if it is 5 degrees, then from the pole, if it is, when it is reflected back, this angle of reflection, angle of incidence, and angle, whatever this angle of incidence is, this will be the angle of reflection. Okay, right? Because obviously that is basically the law, right? Angle of incidence and reflection are going to be same. So obviously you have a ray from here. If you see, we got a from the image, this object came over here. This from the object over here, yeah, a ray comes and hits this pole, so it is reflected back along the with respect to the principal axis, it's reflected along the same angle. Okay, now again this ray, if you see, if this is the reflected ray, so if you extend it, they meet at a point. Now where all of these rays meet, okay, is basically where your image is formed. And one more point to be noticed is any ray that is parallel to the principal axis passes through the focal point. So this ray comes, hits the surface, and it gets reflected back, right? So if you extend this line over here, where they meet, if they extend the line over here, where they meet, this is focal point. Okay, any ray that comes, so this is basically the focal point. Now this is their object. Let's take the object as AB. So over here, this is basically our image that is formed. So what we see in case of a convex mirror, whether you keep the object at infinity or very close to the pole, doesn't matter in where you're keeping this object. Okay, the image, right? The image is always found behind the mirror. Okay, and the image formed is above the principal axis, right? So this is erect. Okay, we call this as erect. Why? See, it is not inverted. Why? The image is formed above the principal axis over here, right? However, the object is also looking the same. It's not inverted, right? If let's say this is the image, if it is formed in this way, right, below the principal axis, it might be inverted, but that's not the case over here. So the image is erect, and if you see, all the rays in this case are basically diverging. So if the rays are diverging, means obviously in this case what we have is a virtual image. Okay, because the rays were extended to meet at this point over here. Now apart from this, what we have is the size of the images, obviously it is smaller than that on the object, which means the size of the image is diminished. Okay, so for a convex mirror, the image formed is erect, virtual, and smaller. Alright, now let's quickly do the convex mirror formula for convex mirror. Alright, very simple one over here. Okay, what we are going to do, we are going to make use of simple geometry. So as I said earlier, a ray AB comes parallel to the parallel to the principal axis, it gets reflected. Okay, because any ray parallel to the principal axis gets reflected along the focal point, right? Any ray that is passing through the center of curvature gets reflected back along the same line. Any ray that passes through this pole over here, again they are reflected, whatever this angle of incidence is, they are reflected along the same angle of reflection. Okay, now in this case, we have given the in this case, this is the object, right? So object distance, if you see, object distance in this case, if you see, we have to take the object distance in this case is BP, right? Object distance BP. If you see, what is this distance over here? What is this distance that we have over here? Right? This distance that we have over here, this is basically U. Okay, BP is nothing but gives us the image distance. Object distance is taken as U, and see, once again, the incident ray is in this direction. The object measurement, all measurement has to be done from the pole. So pole to object, if you go, the distance measurement is in the opposite direction to incident ray. So this is negative. Okay, so next distance that we are going to see is basically image distance. So if you see, which is image distance in this case, if you look at, image distance is basically from the pole to here, okay, from here to here. right, this is image distance, that is BP dash, right, this BP dash is the image distance, okay, and in this case BP dash is nothing but V, okay, and this is incident ray direction, and object distance, if you see, this is V over here, or image distance, again sorry, image distance, we are going in the direction of the incident ray, so it's positive. Okay, so the next value that we are going to see is basically what is the focal length in this case, right? So focal length, if you see, it is from P to F is the focal length, right, from this pole, right, from the pole to this, for this point F is the focal length, and if you see focal length, again this is the incident ray direction, and from the pole you're going in the direction of the incident ray, so focal length is again a positive quantity. Okay, now the last one is radius of curvature. So from the center of the mirror over here, okay, from the pole over here to center of curvature, what we have is basically radius of curvature. This distance is radius of curvature R. Okay, so if this distance is radius of curvature, means incident rays in this direction. To measure radius of curvature, we have to go from in the direction of the incident ray. So PC, center radius of curvature, is again positive value, and we know radius of curvature is twice the focal length. Alright, that's all you need to know to do the mirror formula. Okay, very simple one. Right now what we are going to do, we are going to make use of trigonometry. Now we are going to take two angles over here. Okay, just take, let's take the angle A. Okay, very simple. Sorry, not the angles. What we are going to do is, we are going to take two triangles. That is, we are going to take AB, this object, with respect to center of curvature over here. Okay, we are going to take this as one triangle, and image A dash B dash with respect to center of curvature. We are going to take this one as another triangle. Okay, so we have two triangles over here, that is A dash, okay, that is basically, if you see, we have triangle AB, okay, ABC, this triangle, which is similar to triangle A dash B dash C. Why? If you basically look at this triangle over here, okay, if you basically look at this triangle that we have taken over here, okay, with respect to this triangle A dash B dash C, if you see these two triangles, they both have the same angle over here. If they both have the same angle, means let's take for the first triangle over here, let's take, okay, for the first triangle over here, let's take very simple, for A dash B C, okay, let's take for example the angle as alpha or theta. Okay, any angle, simply for example of that. Okay, try taking tan of theta over here. Tan of theta value will be what? Obviously that would be basically opposite, right? Tan of theta, if you take opposite by, right, that is basically perpendicular by base, right, by BC. Now this triangle, this is for one triangle, we got this. Now again we have another triangle, right? The other triangle we have is A dash B dash C. This also, this is the same angle, right? This has the same angle, again this angle is also theta. So try taking tan of theta for this. You'll have A dash B dash divided by B dash C. Okay, now we have this value over here. Okay, let's rearrange it, right? Now let's keep A dash B dash, okay, to one side, and bring AB down here, which will be equal to on the other side. Okay, on the other side what we are going to do, okay, very simple, let me just do this over here. What we have over here is A dash B dash divided by, okay, divided by AB. Okay, on the other side we will end up having okay, this is AB over here. So on the other side we will end up having, obviously this goes on top, this will be B dash C by BC. Alright, so now what we have is B dash C by BC. Now look at B dash C over here. B dash C, this distance we don't know. Okay, this distance over here, we have no idea what this distance is. But we can take it as BC minus BP dash. Why? This distance we know, right? If you see this case, okay, sorry, we can, this distance we don't know, B dash C we don't know, but what is P to C we know, that is radius of curvature, and what is P to B dash we know. So if you actually see, right, if you actually see in this case, we know this distance, we know this distance, right? So from this distance, if we subtract this distance, we will end up getting, okay, we will end up getting this distance over here, B dash C. Okay, so let's do that in this case. Okay, so all we have to do is very simple. In this case, what is B dash C over here? That will be very simple. We are going to write it as BC, B dash C over here. We are going to write it as PC over here. Okay, PC over here, PC over here. Okay, minus PB dash, minus PB dash. Okay, by, if you see what we have is PC. Okay, so alright, now let's do the numerators. We have PC. Okay, what is PC over here? This is nothing but radius of curvature. Okay, minus PB dash. PB dash is nothing but image distance, that is V. Right, by next what we have is PC over here. Right, so next what we actually have is basically BC. We don't know that distance. BC, the distance, we don't know what is the BC distance over here. But we know what is B to P, that is U. And from P to C, again we know that is radius of curvature. So P to B and P to C over here, we know what it is. Right, so again this denominator, this BC can be written as B to P, BP, okay, plus PC over here. Okay, BP is what? Image distance. Okay, according to sign convention, again it will be negative U. Okay, and PC over here is again radius of curvature. This will be plus R. Okay, now we have two angles over here. Okay, now similarly, if you see, we are going to take one more triangle. Similar to this, we are going to take one more triangle. That is, we are going to end up taking AB. Okay, with respect to P over here. Alright, and another triangle we are going to take is, okay, another triangle we are going to take is ABQ over here. Why? We said this angle, whatever this angle of incidence is, it is equal to the angle of reflection over here. Now, this is principal axis. These two triangles are similar. Okay, so these two triangles are similar. If these two triangles are similar means, now whatever this triangle is, this is principal axis, this is the extended ray. Whatever this angle over here is, okay, whatever this angle over here is, okay, let's say this is angle of reflection. Now, this triangle, this angle over here between this line and this line will also be same. So, if this triangle and this triangle are similar means, and this triangle is angle is equal to the angle over here means, then this triangle will be similar to this triangle. Okay, they both have the same angle. Then angle ABP, triangle ABP over here is basically, or APB over here, right? Or we can say, yeah, the triangle ABP is similar to the triangle A dash P. Why? The angle APB is actually equal to the angle A dash P B dash. Okay, again same consideration as we did earlier. Okay, what we are going to do? We are going to take tan of the angle in this case. For this side, if you take tan of the angle, what will you do? What will you get? You will get AB by BP, right? This is nothing but, yeah, BP over here. For this triangle, A dash BP, if you take the angle, tan of this angle, if you take, that will be A dash B dash, okay, by BP dash, right? So, obviously, we can rearrange this and write, we have A dash B, okay, A dash B dash, okay, by AB we will take it to one side, which is equal to BP, okay, which is equal to PB dash divided by BP. What is PB dash over here? This distance is nothing but image distance V, and it's positive. Why? It's in the direction of the incident ray. And what is BP over here? This is object distance. Object distance is again negative because it is in the distance measurement from pole to the object. We are taking it in the opposite direction, so it's negative. Now we got two values. A dash B dash by AB is V by minus U. Again for this we got A dash B dash by AB is equal to R minus V by minus U plus R. Okay, so I'll just write these two together and let's just solve it. Okay, so we got two values. Now we can equate these two values, right? We have R minus V by minus U plus R, which is actually equal to V by minus U over here. Okay, so we'll cross multiply U into R. Minus into minus will again become plus U into V, which will be, take it to the other side, V into minus U is minus U into V, okay, plus V into R will become VR. UV will take it to the same side. So UV, we will bring this plus UV. This is equal to, this goes to the other side, you become UR plus VR. Okay, so this is 2uv, which is equal to ur plus vr over here. Next, what we are going to do is very simple. We are going to divide both sides. Okay, we are going to divide both sides by we are going to divide both sides by uvr. Okay, each term on both sides we are going to divide by uvr. Obviously, in this case, this gets cancelled. You will have 2 by r, which is equal to, this gets cancelled. You will have 1 by v plus vr over here gets cancelled, 1 by u over here. Okay, earlier we said r is nothing but 2f, right? Twice the focal length. So we'll substitute the same over here. Okay, so if we substitute the same, 2 gets cancelled. So finally what we have, 1 by f is equal to 1 by u plus 1 by v. That's it. There you go. You got your mirror formula. Alright. So with this note, guys, I'm coming towards the end of today's class. On the Unacademy platform also we have free special classes. So the upcoming special classes again are there on the Telegram channel. I would share them live. So go to the app, you can download the app, or you can go to the website, go to self-study, go to free live classes. Okay, all of the upcoming live classes will be there, and again in the live classes we are again going to do some questions with spherical mirrors. Okay, so some concepts we will cover with spherical mirrors, so you can join that class as well. Okay, it's a free class, so you can join. So with this note, I'm ending today's class. I'll see you all in the next class. Do subscribe to the channel, and if you like the video, do share it among your friends. Bye. Take care.